Where did life's building blocks come from? It's one of the most profound questions we can ask. How did the universe, once a vast, lifeless expanse, give rise to the molecules that sparked everything we know? Think about it. Every living thing, from the tallest trees to the tiniest microbes, traces its origins back to those first organic molecules. But how did they form? Was it a cosmic accident, a stroke of unimaginable luck, or something even more mysterious? That's the enigma we're diving into today, exploring 30 mind-bending theories about the birth of life's essential ingredients. Picture this: billions of years ago, long before Earth even existed, the universe was a swirling chaos of dust and gas. Yet somehow, against all odds, the seeds of life emerged. Some scientists believe these molecules arrived on asteroids, hitchhiking across the cosmos. Others argue they were forged in the hearts of dying stars or sparked by lightning in a primordial soup. And then there are the wilder ideas. Could they have been delivered by comets or even sculpted by the invisible hands of quantum physics? The possibilities are as vast as space itself, and each theory opens a door to a new realm of wonder. This journey isn't just about science, it's about unraveling the story of us. Every theory we explore is a piece of the puzzle, a clue to how we came to exist. And here's the thrilling part: we're still discovering new pieces, from lab experiments that recreate the conditions of early Earth to telescopes peering into distant galaxies. The search for answers is alive and evolving. So if you've ever stared up at the night sky and wondered how it all began, you're in the right place. Buckle up, we're about to traverse the cosmos, from the depths of interstellar clouds to the very edges of scientific imagination, to uncover the secrets of the universe's first organic molecules. Could the building blocks of life have hitched a ride to Earth from the far reaches of space? That's the bold claim behind panspermia, the theory that organic molecules didn't originate here at all. They arrived pre-packaged on comets and meteorites. Imagine a time when our solar system was young, bombarded by cosmic debris. Some of those space rocks weren't just barren chunks of rock and metal. They carried the very ingredients life needed to get started. Take the Murchison meteorite, which crashed in Australia in 1969. Inside, scientists found over 90 different amino acids, the same molecules that form proteins in every living organism. Even more striking, some of those amino acids aren't common on Earth, suggesting they formed somewhere else entirely beyond our planet. But space is a brutal environment. Radiation, extreme temperatures, and the vacuum of the cosmos should, in theory, destroy delicate organic compounds. Yet here's the twist: laboratory experiments show certain molecules can survive embedded deep inside asteroids, shielded by layers of rock and ice. Even more compelling, telescopes have detected amino acids floating in giant molecular clouds, the very nurseries where stars and planets are born. It's as if the universe has been scattering these life's ingredients like cosmic breadcrumbs. Still, panspermia isn't without its puzzles. Even if organic molecules survived the journey, how did they withstand the fiery plunge through Earth's atmosphere? Some argue that smaller, carbon-rich meteorites could break apart high up, gently delivering their precious cargo. Others point to comets, whose icy shells might have vaporized upon entry, leaving behind complex molecules in the primordial oceans. But here's the biggest question panspermia leaves unanswered. If life's precursors came from space, where did they come from originally? It's a cosmic version of the chicken and egg dilemma, pushing the mystery one step further into the void. What if the secret to life's origins wasn't in the stars, but hidden deep beneath the ocean? Enter hydrothermal vents, towering, chimney-like structures on the ocean floor, spewing superheated water rich in minerals. These alien-like landscapes might seem inhospitable, but they're teeming with chemical activity, and some scientists believe they could be the cradle where organic molecules first took shape. Unlike the randomness of space, vents offer something crucial: a stable, energy-rich environment where simple ingredients could assemble into life's building blocks. Picture a vent 4,000 meters underwater where scorching, mineral-laden water meets the icy ocean. This extreme contrast creates what chemists call a gradient, a natural battery of sorts where energy flows constantly. That energy could have powered reactions between hydrogen, carbon dioxide, and minerals like iron and sulfur, stitching them together into amino acids and other key molecules. Lab experiments back this up. When scientists recreate vent conditions in pressurized chambers, they've watched simple compounds like formate and acetate emerge spontaneously, the same molecules that form the backbone of more complex organic chemistry. But vents don't just provide energy, they also offer structure. Their porous, rocky surfaces are riddled with microscopic nooks and channels, acting like tiny laboratories where molecules could concentrate and interact. Some researchers compare these spaces to primitive cells, trapping and protecting fledgling organic compounds long enough for them to combine into something more sophisticated. There's even evidence that certain minerals in vents like pyrite can act as catalysts, speeding up reactions that might otherwise take millennia. Yet the vent hypothesis isn't without its gaps. While we've seen simple organics form in simulations, bridging the gap to something as complex as RNA, a molecule many consider essential for life's beginnings, remains a challenge. And then there's the puzzle of timing. Were these vents active early enough in Earth's history to set the stage for life? Still, the idea has a compelling elegance. Instead of relying on cosmic luck, it suggests the planet itself might have had everything needed to cook up life's ingredients, right here in the crushing darkness of the deep sea. The idea that life's ingredients could have brewed right here on Earth in a steamy, lightning-charged primordial soup has captivated scientists for decades. It all traces back to a landmark experiment in 1953, when Stanley Miller and Miller-Urey recreated what they believed was Earth's early atmosphere in a glass flask. The setup was deceptively simple. Water vapor, methane, ammonia, and hydrogen gases thought to dominate the young planet circulated through a chamber where sparks mimicked lightning strikes. After just a week, the water turned murky and analysis revealed something astonishing. The flask was teeming with amino acids, the very molecules that form proteins in every living cell. This electrifying discovery suggested that Earth's violent weather might have jump-started life's chemistry. Picture the planet 4 billion years ago, its skies crackling with storms, its oceans simmering under a dim sun. Every lightning bolt could have been a cosmic chef stirring the broth of existence. The implications were staggering. If basic organic molecules formed this easily, life might not be a rare fluke, it could be a natural outcome of planetary conditions. But science thrives on scrutiny, and over time, doubts emerged. Critics pointed out that Miller and Urey's simulated atmosphere might not match Earth's ancient air. New evidence suggests the early planet had more carbon dioxide and nitrogen, with far less methane and ammonia. When scientists reran the experiment with these revised gases, the yield of organic molecules dropped dramatically. Some argue this undermines the whole premise. If the ingredients were wrong, could the primordial soup still hold water? Yet the story isn't that simple. Later research found that tweaking the conditions, adding volcanic gases or mineral surfaces, could boost organic production even in the updated atmosphere. And here's the twist: amino acids have been discovered in places no one expected, like inside ancient meteorites and around distant stars. This raises a tantalizing question. Could the truth lie somewhere in between? Perhaps Earth's atmosphere contributed some building blocks while cosmic deliveries supplied others. The Miller-Urey experiment remains a cornerstone, not because it got everything right, but because it dared to ask how chemistry becomes biology. It showed that under the right conditions, the leap from simple molecules to life's precursors isn't just possible, it might be inevitable. and that revelation still echoes today, reminding us that sometimes the most profound answers begin with a spark in a flask. Imagine the vast, frigid spaces between stars, regions so cold that most chemical reactions should grind to a halt. Yet somehow, against all odds, these icy voids are teeming with complex organic molecules. How is this possible? The answer might lie in something deceptively simple: cosmic dust. These microscopic grains, no larger than smoke particles, could have been the universe's earliest chemistry labs, providing the perfect surfaces for life's building blocks to assemble in the deep freeze of space. Interstellar dust isn't just inert debris, it's incredibly active. Each grain is a mosaic of minerals like silicates and carbon, often coated in layers of ice made of water, methane, and ammonia. In the extreme cold of molecular clouds, where temperatures hover just above absolute zero, these ices become sticky traps for wandering atoms and molecules. Over eons, simple compounds like carbon monoxide or formaldehyde accumulate on the dust surface, held in place by the icy matrix. Then, something remarkable happens. Cosmic radiation, high-energy particles streaming through space, hits these ices, breaking molecular bonds and triggering reactions that would never occur under normal conditions. It's chemistry in slow motion, powered by the universe itself. Astronomers have detected the results of this process in stunning detail. Giant molecular clouds like the one in Orion's belt are veritable factories of organic molecules. Telescopes have picked up signatures of everything from ethanol to glycine, the simplest amino acid floating in these regions. Some of these molecules are surprisingly large, with chains of 10 or more atoms. That complexity shouldn't exist in such harsh environments, unless something is giving chemistry a helping hand. Dust grains seem to be that missing piece, acting as both a scaffold and a catalyst. Their rough surfaces provide anchor points for molecules to meet and react, while their icy coatings shield delicate compounds from destructive radiation. Laboratory experiments back this up. When scientists recreate space conditions in vacuum chambers, chilling mixtures of gases to near zero temperatures and bombarding them with radiation, they've watched complex organics form on synthetic dust grains. Even more intriguing, some of these experiments produce molecules with a curious property. They're handed, meaning they exist in mirror image forms, just like the amino acids in living things. Life on Earth uses only one version of these molecules, raising the spine-tingling possibility that this preference might have been seeded by cosmic dust billions of years before life began. Yet mysteries remain. How do these fragile molecules survive the journey from deep space to planets? Some theories suggest dust grains could clump together inside comets, sheltering their precious cargo until they collide with young worlds like Earth. Others propose that ultraviolet light from nearby stars might gently nudge organic, rich dust into planetary systems. Whatever the path, the implications are staggering. If dust grains really did catalyze life's ingredients, the universe might be primed for life everywhere, quietly assembling the pieces in the darkness between the stars. Ultraviolet light, often seen as a destructive force that damages DNA and breaks down molecules, might hold a surprising secret about life's origins. While it's true that intense UV radiation can tear substances apart, it can also build them up under the right conditions. Picture the vast, icy clouds drifting between stars where dust grains are coated in frozen layers of water, methane, and ammonia. When UV photons from nearby stars slam into these ices, they don't just shatter molecules. They rearrange them, sparking reactions that craft complex organic compounds from simple ingredients. Laboratory experiments reveal just how powerful this process can be. Scientists have recreated space-like conditions in vacuum chambers, freezing mixtures of common cosmic gases onto cold surfaces, then bombarding them with UV light. The results, molecules like nucleobases, the very building blocks of DNA and RNA, emerged spontaneously. In one striking experiment, researchers exposed a mix of water, ammonia, and hydrogen cyanide to UV radiation, and within days they detected uracil and cytosine, two of the 4 key nucleobases found in RNA. These aren't just random chemicals, they're fundamental to life as we know it, suggesting that the universe might have been quietly assembling life's blueprints long before planets even formed. The magic lies in those icy mantles coating dust grains. Far from being inert, these frozen layers act like tiny chemical reactors. When UV light hits them, it knocks electrons loose, creating reactive fragments that eagerly bond with nearby molecules. The ice itself plays a crucial role, trapping these fragments long enough for them to combine into more complex structures. Without the icy matrix, the fragments would simply drift apart, but the frozen surface keeps them in close quarters, turning the grain into a microscopic factory for organic synthesis. But here's the twist. UV radiation doesn't just create these molecules, it also helps them survive. In the harsh environment of space, newly formed compounds would quickly disintegrate under relentless radiation. Yet the icy mantles shield them, absorbing destructive energy while allowing the constructive reactions to continue. It's a delicate balance, like a cosmic game of chemistry where destruction and creation dance in tandem. Astronomers have spotted evidence of this process in action. Observations of young star systems show that regions bombarded by UV light often contain higher concentrations of complex organics. Even more compelling, some of these molecules exhibit a curious preference for one mirror image form over another, a trait seen in biological molecules on Earth. Could the same UV-driven chemistry that crafted nucleobases in space have given life its initial bias toward certain molecular shapes? Yet questions linger. How do these fragile molecules survive the journey from interstellar clouds to planetary surfaces? Some might hitch rides inside comets, protected by layers of ice until they crash into planets like Earth. Others could be gently delivered by cosmic dust, sifting down through atmospheres over millennia. Whatever the path, the idea that UV light, a force we often associate with sterilizing surfaces, might have been a hidden architect of life's ingredients adds a thrilling layer to the mystery. It suggests that the universe doesn't just tolerate life's precursors. In the quiet chill of space, it might be actively assembling them one photon at a time. Volcanoes, nature's fury unleashed, might seem like the last place life's delicate building blocks could emerge. Yet these fiery giants could hold the key to one of the most compelling theories about organic molecules. Picture the early Earth, its surface riddled with erupting volcanoes, spewing not just lava but a cocktail of gases: methane, ammonia, carbon dioxide, and hydrogen sulfide. These weren't just destructive forces, they were chemical reactors on a planetary scale, churning out the raw materials for life in their scorching plumes. Modern volcanic sites offer tantalizing clues. Take Iceland's geothermal fields, where steam vents and bubbling mud pots teem with chemical activity. Scientists sampling these areas have detected simple organic compounds like formic acid and formaldehyde molecules that can link together to form more complex structures. Even more striking, volcanic lightning, jagged bolts crackling through ash clouds, could have acted like a natural version of the Miller-Urey experiment, zapping volcanic gases into amino acids. The energy for life's chemistry might have come not from gentle tides or sunlight, but from the very eruptions that once made Earth seem hellish. But how does this process work? Deep underground, volcanic heat and pressure can force gases like methane and ammonia to react, forming organic molecules even without lightning spark. Hydrothermal systems near volcanoes add another layer. As scalding water percolates through mineral-rich rock, it dissolves metals like iron and nickel, which can act as catalysts, molecular matchmakers that help simple compounds bond into more complex ones. Some researchers have recreated these conditions in labs, heating volcanic gas mixtures with minerals and watching as organics emerge, almost like a recipe for pre-life chemistry written in Earth's fiery heart. Yet volcanoes aren't just producers, they're also protectors. Lava flows and ash layers could have shielded fragile organic molecules from harsh ultraviolet radiation in Earth's early atmosphere. Pumice, the lightweight, porous rock ejected during eruptions, might have played an unexpected role too. Its countless tiny holes create vast surface areas where molecules could concentrate and interact, turning each floating chunk into a potential micro-laboratory. The implications are profound. If volcanoes were indeed organic factories, then planets with active volcanism, like Mars in its wetter past, or even distant exoplanets, might have similar potential to brew life's ingredients. It's a reminder that creation and destruction are two sides of the same coin. The same forces that can wipe out life might have been the very ones that made it possible in the first place. Among the swirling chaos of early Earth, an unlikely hero might have quietly shaped life's earliest molecules: clay. Not just any dirt, but mineral-rich clays with surfaces so finely structured they could have acted as nature's first blueprints. Picture a microscopic landscape of charged layers, each one attracting and aligning simple organic molecules like a molecular assembly line. This isn't science fiction. Decades of experiments reveal that certain clays, like montmorillonite, don't just sit there. They actively participate in chemistry, accelerating the formation of complex molecules that life would later depend on. Take RNA, the molecule many scientists believe was life's original genetic material. Building RNA from scratch requires linking smaller units called nucleotides into long chains, a process that, in water, should be nearly impossible without help. But when researchers mix nucleotides with clay particles, something remarkable happens. The clay's charged surfaces grab hold of the nucleotides, holding them close enough to bond. In some experiments, clays have catalyzed the formation of RNA strands over 50 units long. That's not random chemistry, it's molecular craftsmanship, suggesting these humble minerals might have been Earth's first editors, stitching genetic code before biology even existed. Clays excel at this because of their unique structure. Their layers are riddled with tiny gaps and imperfections, creating pockets where molecules can nestle and react. Some clays even contain metals like zinc or iron, which can act as catalysts, lowering the energy needed for bonds to form. It's like having a built-in toolkit, each clay particle a miniature factory churning out order from chaos. But the magic doesn't stop there. Clays could also have solved one of the biggest puzzles in origin of life research: concentration. In the vast dilute soup of early oceans, how did molecules find each other? Clay's charged surfaces act like molecular Velcro, gathering and concentrating scattered organics. Imagine tide pools where water evaporates, leaving behind dense mixtures of chemicals. Except instead of sunlight doing the work, it's the electrostatic pull of mineral surfaces. Critics point out that while clays assist in forming molecules like RNA, they don't explain how those molecules eventually took over their own replication, a key step toward life. Yet recent experiments hint at an answer. Some clays can not only assemble RNA but also protect it from breaking apart, even encouraging rudimentary copying. It's as if the mineral world was gently nudging chemistry toward biology, one sticky layer at a time. The implications stretch beyond Earth. Mars' ancient clay-rich regions, like those explored by the Curiosity rover, could have offered similar conditions. If clay templates really did jumpstart life here, why not there? It's a humbling thought that the soft, crumbling Earth beneath our feet might hold the secret to existence itself, a relic of a time when chemistry began dreaming of becoming life. Lightning crackling through Earth's ancient skies might have been more than just a spectacular light show. It could have been the spark that lit the fuse of life itself. While the Miller-Urey experiment first hinted at this idea decades ago, newer research reveals just how dynamic these electric discharges could be. Imagine the young planet, its atmosphere thick with water vapor, nitrogen, and carbon dioxide, constantly electrified by storms. Every bolt wasn't just a flash of energy, it was a miniature reactor splitting molecules apart and forging them into something new. Recent experiments have taken this concept far beyond the classic flask setup. Scientists now use pulsed plasma discharges, precise, laser-like bursts of electricity, to simulate lightning strikes with astonishing accuracy. In one study, these controlled zaps transformed simple gases like nitrogen and carbon monoxide into formic acid and formaldehyde, compounds essential for building sugars and amino acids. Even more striking, some setups have produced pyruvic acid, a key player in the metabolic processes that power living cells. It's as if lightning wasn't just a random force of nature, but a deliberate architect of life's chemistry. But here's the twist: the power of these discharges isn't just in their energy, it's in their unpredictability. Unlike steady heat or gentle chemistry, lightning delivers chaotic, intense bursts that create wildly varied conditions. This turbulence might actually be crucial. Think of it like a chef searing a steak at high heat. The sudden temperature spike triggers reactions that slow cooking can't replicate. Similarly, the rapid heating and cooling around a lightning bolt could have driven reactions that calm, stable environments would never permit. The environment matters too. Early Earth's lightning likely crackled over volcanic landscapes or through ash-laden skies, adding sulfur and metals to the mix. Lab experiments show that when sulfur compounds are present, electric discharges produce even more diverse organics, including thiol sulfur containing molecules critical for enzyme function. And if those bolts struck near tidal pools or shallow waters, the resulting compounds could have washed into concentrated pools, creating ideal nurseries for the next steps toward life. Yet the most fascinating revelation comes from studying not just the lightning but what follows. After the discharge, the real magic happens in the cooling aftermath. As the superheated air contracts, it forms tiny aerosols, microscopic droplets rich in organics. These could have acted as primitive cells, trapping and protecting fragile molecules while they combined into more complex structures. Some researchers call this the thunderstorm reactor model, where each storm wasn't just a momentary event, but a cyclical factory, churning out batches of prebiotic ingredients with every passing cloudburst. Of course, gaps remain. While we've seen lightning create life's building blocks, assembling them into something as intricate as RNA or a self-replicating system is another challenge entirely. And not all scientists agree on how much of Earth's early organics came from sparks versus other sources like hydrothermal vents or space dust. But the evidence is compelling enough that astrobiologists now consider lightning a key ingredient in the recipe for life. Not just here, but perhaps on other stormy worlds with the right atmospheric cocktail. So the next time you see a lightning bolt split the sky, remember, it's not just nature's fireworks. It might be the echo of a process that 4 billion years ago helped turn a lifeless planet into a living one. Deep beneath Earth's surface, where sunlight never reaches, another powerful force could have been quietly assembling life's ingredients: natural radioactivity. Picture a subterranean world where water seeps through rock fissures, passing dangerously close to radioactive minerals like uranium or thorium. These elements emit invisible but relentless energy, breaking apart water molecules with a process called radiolysis. But destruction here is only half the story. As water splits into hydrogen and reactive fragments, those fragments collide with dissolved carbon dioxide or nitrogen, forging entirely new compounds. What starts as chaos becomes a surprising act of creation, one that might have built organic molecules without sunlight, lightning, or even volcanic heat. Experiments with gamma radiation, the same type emitted by radioactive rocks, show just how efficient this process can be. When scientists blast mixtures of water, carbon dioxide, and nitrogen with controlled radiation, they've observed the formation of formate, acetate, and even amino acids like glycine. These aren't just random byproducts, they're keystones of biochemistry. The key lies in the energy's slow, steady release. Unlike a lightning bolt's instantaneous surge, radioactive decay delivers a constant drizzle of energy, allowing molecules to rearrange step by step. It's chemistry at a glacial pace, but over millions of years, that patience could have paid off in a big way. One remarkable study focused on Oklo, a natural nuclear reactor in Gabon where uranium deposits sustained fission reactions 2 billion years ago. While too late for life's origins, the site proves how long such processes can persist and how they alter their surroundings. Analysis of nearby minerals revealed traces of altered organic material, hinting at radiation's ability to reshape chemistry even in solid rock. Now imagine similar but far older deposits on early Earth, their radiation quietly churning out organics in groundwater pools or wet sediment layers. But radioactivity's role might go beyond mere synthesis. Some researchers propose it could have also provided the perfect environment for life's next steps. Radiation creates gradients pockets of varying chemical concentrations that could have acted as primitive energy sources, much like modern cells use proton gradients to power themselves. And let's not forget shielding. Deep underground, these reactions would have been protected from the violent surface conditions of the young Earth, offering a stable workshop for delicate molecules to experiment with complexity. Critics argue that radiation's destructive power might outweigh its creative potential, but nature has a way of balancing both. Just as ultraviolet light can both break and build molecules in space, radioactivity's dual nature might have been essential. The same particles that shatter bonds also provide the energy and raw materials to form new ones. It's a reminder that life's origins might not hinge on a single pleasant environment, but on the dynamic interplay between harsh forces, each one carving out opportunities for chemistry to cross into biology. If this theory holds, it expands the range of places where life could arise. Mars, for instance, has vast uranium deposits and evidence of ancient groundwater. Europa's icy shell might conceal radioactive hotspots deep beneath its ocean. Even planets far from their suns could harbor subsurface radiolytic oases, turning what we once considered dead zones into potential incubators for life's first whispers. Comets have long been considered the cosmic couriers of life's essential ingredients, but their role might be even more profound than we once thought. These icy wanderers don't just carry organic molecules, they deliver the very medium that brings those molecules to life, water. Imagine a young Earth still cooling from its violent formation, its surface scorched and dry. Then, like a celestial rainstorm, comets begin pelting the planet, each impact releasing torrents of water alongside a cargo of prebiotic chemicals. This dual delivery system could have transformed our world from a barren rock into the vibrant blue cradle of life we know today. The Rosetta mission study of comet 67P Churyumov-Gerasimenko unveiled startling evidence. This rubber duck-shaped ice ball, billions of miles from the sun, was found to contain not only water vapor but also a cocktail of organic compounds, glycine, phosphorus, and even formaldehyde. What makes this discovery so groundbreaking is the ratio of heavy water, a variation of H2O with an extra neutron found on the comet. Earth's oceans and 67P share a strikingly similar composition, suggesting a shared origin story. It's as if comets like this one were custom-built to stockpile the exact ingredients needed for life's recipe. But how do these fragile molecules survive the brutal journey? Comets are more than just dirty snowballs. Their interiors are layered like cosmic onions, with organic, rich dust encased in thick shells of ice. As a comet approaches the sun, its outer layers vaporize, but the core remains insulated, protecting its precious cargo until impact. When these icy projectiles slammed into Earth's early atmosphere, their water would have condensed into steam clouds, later falling as rain, while their organic payloads dissolved into the newborn oceans. The heat of entry might seem destructive, but simulations show brief, intense heating could actually catalyze new reactions, turning simple cometary organics into more complex structures upon landing. Critics argue that comets alone couldn't have supplied all of Earth's water. Their deuterium ratios don't perfectly match, yet they might not have acted alone. Combine cometary delivery with water-rich asteroids and volcanic outgassing, and suddenly the puzzle pieces fit. Each source could have contributed different components, with comets bringing critical organics alongside their watery gifts. The implications stretch far beyond Earth. If comets seeded our planet, they could have done the same for Mars, Europa, or even exoplanets in distant systems. Every icy visitor from the Oort cloud might be a potential life-bringer, whispering the same ancient message across the cosmos. Where there is water and organics, the leap to life might not be a matter of if but when. Formaldehyde might not sound like the most glamorous molecule. After all, it's best known for preserving biological specimens, but out in the cold expanse of space, it's a cosmic celebrity. Astronomers have detected this simple compound floating in vast molecular clouds, the same nurseries where stars and planets are born. At first glance, that might not seem remarkable, but here's the twist. Formaldehyde could be the missing link in one of life's most crucial chemical pathways. Under the right conditions, it can transform into sugars like ribose, the very backbone of RNA, the molecule many scientists believe was life's first genetic material. The discovery of formaldehyde in space dates back to the 1960s, when radio telescopes first picked up its telltale signature in the Orion Nebula. Since then, it's been found everywhere from the dusty arms of our own galaxy to the distant reaches of interstellar space. What makes it so special isn't just its abundance, it's its versatility. Formaldehyde acts like a molecular Swiss Army knife, capable of reacting with other common space chemicals to form more complex structures. In lab experiments simulating cosmic conditions, scientists have watched formaldehyde molecules combine into glycoldehyde, a simple sugar, and then into ribose under ultraviolet light or catalytic minerals. It's as if the universe handed life a ready-made kit for building genetic material. This process dovetails perfectly with the RNA world hypothesis, the idea that before DNA or proteins, RNA ruled the primordial Earth. RNA is uniquely capable of both storing genetic information and catalyzing chemical reactions, a dual talent that could have made it the star player in life's earliest days. But there's always been a puzzle. How did ribose, RNA's sugar component, form in significant quantities? Earth's early oceans would have diluted prebiotic soups, making it hard for ribose to accumulate. That's where interstellar formaldehyde comes in. If ribose's precursors were already raining down on Earth from space, concentrated and ready to assemble, the odds of RNA emerging skyrocket. Recent studies add even more intrigue. When researchers exposed frozen formaldehyde mixtures to conditions mimicking asteroid interiors, moderate heat and slight pressure, they observed not just ribose but its close cousin, deoxyribose, the sugar in DNA. This suggests the same cosmic chemistry that might have sparked RNA could have also laid the groundwork for its more stable successor. Even more astonishing, some of these sugar-forming reactions produce molecules with a slight-handedness, a preference for one mirror image form over another, just like the sugars in living organisms. Yet mysteries linger. While we've seen formaldehyde transform into sugars in labs, doing so in the real chaos of space or early Earth is another challenge. Could interstellar radiation have provided the necessary energy without destroying the delicate products? Did mineral surfaces on asteroids or comets act as cosmic workbenches, guiding these reactions toward complexity? Every answer leads to new questions, but one thing is clear. What we once dismissed as a humble preservative might actually be one of the universe's master architects, quietly assembling the pieces of life in the frozen darkness between the stars. Far beyond Earth, shrouded in an orange haze thicker than smog over a megacity, Saturn's moon Titan hides a secret recipe for organic chemistry. This frozen world, where methane rains from the sky and ethane flows in rivers, might seem like an unlikely cousin to early Earth until you meet the tholins. These bizarre tar-like molecules, named after the Greek word for muddy, are what give Titan its eerie orange glow, formed when sunlight fractures methane and nitrogen high in the Moon's atmosphere. Tholins are more than just cosmic pollution. They're chemical chameleons capable of transforming into the very building blocks of life under the right conditions. And here's the startling part. Lab experiments show that what's happening on Titan today might mirror the processes that kick-started life on our own planet billions of years ago. To understand tholins, picture Titan's upper atmosphere as a sprawling cosmic kitchen. Ultraviolet light from the distant sun acts like a blender, breaking apart methane and nitrogen molecules into reactive fragments. These fragments collide and stick together, forming increasingly complex chains, a process scientists call polymerization. The result, a sticky organic haze that slowly drifts down to Titan's surface, coating its icy dunes and methane lakes in a layer of primordial goo. What makes this so fascinating is that when researchers recreate Titan's atmosphere in vacuum chambers mixing nitrogen, methane, and a dash of energy from plasma arcs or UV lamps, they don't just get tholins. Over time, these experiments yield amino acids like glycine and alanine, the same molecules that form proteins in every living cell on Earth. But Titan's haze isn't just a passive ingredient list, it's an active participant in chemistry. Unlike Earth's atmosphere today, Titan lacks free oxygen, making it eerily similar to our planet's air before life began. In this oxygen-free environment, tholins behave differently than they would on modern Earth. Some experiments suggest that if Titan's tholins landed in warm water, say, from a volcano erupting beneath the Moon's icy crust, they could break down into even more biologically relevant molecules like nucleotide bases or phospholipids. It's as if Titan's entire atmosphere is a factory, endlessly producing the raw materials for life, then depositing them onto a frozen conveyor belt of hydrocarbons. The parallels to early Earth are uncanny. 4 billion years ago, our planet might have sported a similar orange haze created by sunlight acting on methane and nitrogen. Unlike Titan, Earth had one crucial advantage: liquid water oceans. If tholins rained into those ancient seas, the combination of water, heat, and minerals could have supercharged their transformation into more complex organics. Some researchers even propose that Titan's chemistry offers a snapshot of what Earth's prebiotic atmosphere looked like before life rewrote the rules, a preserved relic of a cosmic process that here led to biology. Yet Titan isn't just a time capsule, it's a testbed for universal possibilities. If tholins can form amino acids in a world as cold as -180 degrees Celsius, what does that say about the potential for life's ingredients to arise across the cosmos? The upcoming Dragonfly mission, set to land a drone-like rover on Titan in the 2030s, aims to find out. Equipped with mass spectrometers, it will sniff out tholins on the surface, analyzing their composition in ways lab experiments never could. Who knows, we might discover that this alien sludge is even more sophisticated than we imagined, a reminder that the universe's recipe for life's building blocks might be written in more languages than we've yet learned to read. Deep beneath Earth's crust, where pressures crush rock into flowing currents and temperatures rival the sun's surface, lies a hidden carbon treasure trove that might have played a starring role in life's origin story. While we often think of volcanoes as destroyers, their roots tap into a vast underground network of carbon-rich reservoirs, molten rock infused with graphite, diamonds, and even methane. When these materials erupt to the surface, they don't just spew lava, they deliver raw ingredients that could have jump-started organic chemistry on the young Earth. Recent studies of kimberlite pipes, ancient volcanic conduits that ferry mantle material upward, reveal something astonishing. Trapped within these diamond-bearing rocks are microscopic pockets containing not just carbon, but complex hydrocarbons like ethane and propane. These aren't contaminants from near the surface, Their unique isotopic signatures prove they formed deep within the mantle, under conditions once thought impossible for organic molecules to survive. It's as if Earth itself has been cooking carbon compounds in its subterranean kitchen for billions of years, occasionally serving them up through volcanic vents like a cosmic waiter delivering life's appetizers. The mechanism behind this deep carbon factory is both elegant and powerful. Under extreme heat and pressure, minerals like olivine react with carbon dioxide and water in a process called serpentinization. This not only produces hydrogen gas, a key energy source for early life, but also generates methane and other simple organics. Laboratory experiments using diamond anvil cells to mimic mantle conditions have confirmed that these reactions can create acetic acid and even pyruvate, molecules central to modern metabolism. Imagine hydrothermal systems like the Lost City vents, but operating dozens of kilometers underground, where geochemical forces turn rock and gas into prebiotic cocktails. What makes this theory so compelling is its ability to solve multiple puzzles at once. Unlike delivery from space or surface-based synthesis, deep carbon reservoirs would have been shielded from Earth's violent early bombardments, providing a stable, long-term source of organics. They also explain the abundance of certain carbon isotopes found in ancient rocks, isotopes that match mantle signatures rather than extraterrestrial ones. And here's the kicker: this process isn't unique to Earth. Mars' extinct volcanoes and even Jupiter's moon Io might have similar carbon-rich plumbing, suggesting the recipe for life's ingredients could be written into the very architecture of rocky planets. Yet mysteries remain. How do these deep-sourced molecules survive their fiery ascent? Some researchers propose that rapid eruption speeds and insulating magma chambers act like a molecular fast pass, shielding organics from complete destruction. Others point to volcanic gases like carbonyl sulfide, which can protect fragile compounds by forming stable complexes. Whatever the mechanism, the implications are staggering. If Earth's mantle truly is a carbon bakery, then planets we once wrote off as lifeless might just need the right volcanic recipe to start cooking. High above Earth's ancient surface, long before the first breath of oxygen filled the air, a thick, orange haze might have draped the planet like a chemical veil, one that didn't just obscure the young sun's light, but actively sculpted the building blocks of life. This photochemical smog, a swirling cocktail of organic molecules, could have been far more than atmospheric decoration. Like a cosmic greenhouse, it may have shielded fragile compounds from destructive ultraviolet radiation, while simultaneously concentrating them into richer, more complex mixtures. To understand how this worked, scientists are turning to an unlikely laboratory. Saturn's moon Titan, where a similar haze still churns today, offering a glimpse into Earth's possible prebiotic past. Titan's atmosphere is a chemist's fever dream, a place where methane and nitrogen, bombarded by sunlight, transform into vast clouds of tholins and other organic aerosols. These particles don't just float, they clump together, growing heavier until they rain down onto the moon's surface, coating its icy dunes in a sticky layer of prebiotic goo. Now imagine Earth 4 billion years ago, its skies rich in methane and carbon dioxide, its surface bathed in far more intense UV light. Under those conditions, simulations show that photochemical smog would have formed even more readily, creating a global haze that acted like a giant chemical reactor. The smog's particles could have served as tiny sponges, absorbing and concentrating simple molecules like hydrogen cyanide and formaldehyde compounds that, on their own, might have been too dilute to react in the open air. But here's where it gets clever. While the haze blocked harmful UV rays, it didn't eliminate energy entirely. Instead, it diffused sunlight into gentler, longer wavelengths, creating a Goldilocks zone for chemistry, not too harsh to destroy delicate organics, but not too weak to prevent reactions. Lab experiments mimicking these conditions have produced startling results. When scientists irradiate methane-nitrogen mixtures with simulated early Earth sunlight, they observe the formation of not just smog, but nucleobases like adenine, key components of DNA and RNA. Even more intriguing, the haze particles themselves can act as catalysts, their complex surfaces providing scaffolding for molecules to align and bond in ways that would be impossible in open air. The parallels to Titan are striking, but Earth's smog might have had an extra advantage: water. As haze particles grew heavy and descended, they could have plunged into shallow ponds or tidal zones where water acted as a solvent, dissolving and rearranging their organic cargo. This cycle, uplift into the smog layer, chemical enrichment, then rain out, might have repeated for millions of years, each iteration adding complexity to the molecular brew. Some researchers compare it to a planetary-scale version of the Miller-Urey experiment, with the entire atmosphere as the flask and sunlight as the spark. Yet this theory isn't without its shadows. Critics point out that too much haze could have cooled the planet excessively, creating a young Earth freeze that might have slowed chemical reactions. Others argue that while smog can create molecules, it doesn't necessarily explain how they organized into self-replicating systems. Still, the idea holds a compelling elegance. It suggests that life's precursors didn't need to rely solely on lightning strikes or hydrothermal vents. The sky itself could have been a factory, its swirling oranges and browns not just a barrier to the sun, but a cradle for the first whispers of chemistry becoming biology. And if that's true, the implications stretch beyond our own planet. Exoplanets with hazy atmospheres, once dismissed as uninhabitable, might instead be ideal incubators for organic chemistry. The very thing that makes their skies opaque could be the signature of a hidden alchemy, one that, given time and the right conditions, might quietly stir the same recipe that once turned our pale blue dot into a living world. Asteroid impacts are often painted as apocalyptic events, world-ending catastrophes that scorch the sky and boil the seas. But what if these violent collisions weren't just destroyers? What if, in the chaos of shattered rock and superheated air, they were also creators, forging the very molecules life needed to begin? This is the heart of meteorite impact synthesis, a theory that turns our view of cosmic collisions upside down. Picture a massive asteroid slamming into early Earth, its unimaginable energy vaporizing rock and metal on contact. In the microseconds after impact, temperatures soar past 2,000 degrees and shockwaves ripple through the surrounding landscape. Yet within that inferno, something remarkable happens. The intense heat and pressure don't just break molecules apart. They force simple elements like carbon, hydrogen, and nitrogen to recombine into complex organics. Take Canada's Sudbury Basin, one of Earth's oldest and largest impact craters. Formed nearly 2 billion years ago, this sprawling scar isn't just a geological curiosity, it's a time capsule. The site is laced with metal-rich deposits, including nickel and copper, but what's truly fascinating is what scientists have found trapped within them. Analyzers reveal traces of hydrocarbons and even amino acids embedded in the impact melt. These molecules couldn't have survived the collision intact, which means they must have formed during the event, cooked into existence by the very forces that seemed destined to obliterate them. Laboratory experiments have recreated these extreme conditions using high-powered guns to simulate impact shocks. When researchers fire projectiles into mixtures of water, ammonia, and carbon, ingredients common on the early Earth, the resulting splashes contain a surprising array of organics. The secret lies in the shockwaves themselves. As they propagate through the target material, they create fleeting pockets of extreme pressure and heat, where chemical bonds snap and reform in unfamiliar ways. It's like a molecular game of musical chairs, with atoms scrambling to find new partners in the chaos. Some of these configurations, against all odds, turn out to be the precursors of life. But impacts offer more than just heat and pressure. They also deliver raw materials. many asteroids are rich in metals like iron and nickel, which can act as catalysts guiding wayward molecules toward complexity. When a metal-laden meteorite strikes, it doesn't just bring energy, it brings the tools to harness that energy constructively. Even the molten rock left behind, known as impact melt, plays a role. As it cools, it forms porous structures teeming with microscopic chambers, each one a potential incubator where organics could concentrate and interact. Here's the twist. Impacts might have been especially fruitful in Earth's early days, when the planet was still a moving target in a cosmic shooting gallery. Back then, collisions weren't rare disasters, they were regular events, each one a potential chemistry set raining from the sky. And while we often think of water as life's essential solvent, impact sites add another layer. The sudden heat could have vaporized surface water, but it also might have melted subsurface ice, creating temporary hot springs rich in freshly minted organics. These oases wouldn't have lasted forever, but in the span of millennia, they could have been enough to tip the scales toward biology. Critics argue that the very violence of impacts would outweigh their creative potential, but nature has a way of balancing extremes. Just as wildfires clear the way for new growth, cosmic collisions could have been the universe's brutal yet effective way of stirring the pot. The lesson from Sudbury and lab experiments isn't that impacts are gentle, it's that even in destruction, the seeds of creation are hiding, waiting for the right conditions to sprout. So the next time you look at the moon's pocked surface, remember, those craters aren't just scars, they might be the fingerprints of the universe's most unexpected alchemists. Far from the scorching black smokers that dominate deep-sea hydrothermal systems, another kind of vent thrives in the ocean's depths, one that trades blistering heat for something far more subtle yet equally powerful: chemistry. The Lost City hydrothermal field, discovered in the Atlantic Ocean in the year 2000, is unlike any other vent system on Earth. Instead of spewing superheated, acidic plumes, these towering limestone chimneys gush warm, alkaline fluids rich in hydrogen and minerals. And it's this gentle but persistent chemical imbalance, scientists believe, that could have provided the perfect conditions for life's molecules to emerge without the need for extreme temperatures. At the heart of this theory lies a simple but profound idea: gradients. Where black smokers rely on volcanic heat to fuel reactions, alkaline vents harness the natural tension between their basic fluids, with pH levels as high as 9 or 10, and the more acidic seawater around them. This contrast creates a kind of electrochemical battery where protons flow from the acidic ocean into the alkaline fluids inside the vents. That flow isn't just energy, it's a built-in driver for chemistry, pushing hydrogen and carbon dioxide together to form simple organic compounds like formate and acetate. It's as if the vents themselves are breathing, inhaling raw materials and exhaling the precursors of life. What makes Lost City so compelling is its longevity. While traditional hydrothermal vents last perhaps a few decades before collapsing, alkaline vent systems can persist for tens of thousands of years. Their chimneys grow slowly, layer by mineral layer, creating intricate networks of microscopic pores and channels. These spaces aren't just passive structures, they act like primitive cells, trapping and concentrating molecules while the pH gradient does the work of stitching them together. In lab experiments, scientists have recreated these conditions using simulated vent materials, watching as bubbling alkaline solutions spontaneously generate not just organics but also tiny, bubble-like structures that mimic cell membranes. The real magic, though, might lie in the vent's mineral makeup. Unlike their volcanic cousins, alkaline vents are rich in iron-sulfur minerals like green rust and maconite. These aren't just bystanders, they're active participants, capable of catalyzing reactions that turn simple molecules into more complex ones. Some studies suggest these minerals could even facilitate the formation of acetyl phosphate, a molecule that modern cells use to store energy. It's a tantalizing hint that the same chemistry powering life today might have gotten its start in these labyrinthine rock formations. But the alkaline vent hypothesis isn't without its skeptics. Critics point out that while these systems excel at producing simple organics, bridging the gap to something as intricate as RNA, a molecule many consider essential for life's origins, remains a challenge. Others question whether early Earth's oceans were acidic enough to create the necessary pH gradients. Yet recent discoveries keep tipping the scales in lost cities' favor. Hydrothermal fields with similar chemistry have been found near the mid-Atlantic ridge, suggesting these systems aren't one-offs but part of a broader geologic phenomenon. And if they existed 4 billion years ago, their quiet, persistent chemistry might have been the universe's way of whispering to the building blocks of life, "Take your time." The right conditions will last, so next time you picture life's beginnings, don't just imagine violent storms or scalding vents. Think of the slow, patient work of alkaline seeps, their mineral veins humming with quiet energy, their labyrinthine chambers offering shelter, their chemistry unfolding not in a flash but over millennia. After all, life didn't need a single dramatic moment to begin. It might have needed exactly the opposite, a place where time itself was an ally. Sulfur might not smell like the secret ingredient for life. Its rotten egg stench hardly suggests cosmic importance. Yet this yellow element could have been the unsung hero in life's origin story, acting as both matchmaker and fuel for the earliest organic reactions. Picture Earth 4 billion years ago, its volcanic landscape spewing not just lava, but plumes of sulfur dioxide and hydrogen sulfide into a primitive atmosphere. These weren't just toxic gases, they were chemical powerhouses capable of jump-starting reactions that turned simple molecules into life's precursors. Modern metabolism offers clues to sulfur's ancient role. Deep within your cells right now, iron-sulfur clusters, tiny molecular assemblies, help convert food into energy. These structures are so fundamental that they're found in everything from bacteria to blue whales, hinting at an evolutionary relic dating back to life's very beginning. But how did sulfur go from volcanic exhaust to biological cornerstone? The answer might lie in hot springs like those in Iceland's Hydrothermal Valley, where sulfur-rich waters simmer at the edge of boiling. When scientists simulate these environments in labs, mixing volcanic gases with iron-rich minerals under heat and pressure, something remarkable happens. Sulfur acts as a chemical bridge, helping carbon dioxide and hydrogen combine into formate, a simple organic acid that's a stepping stone to more complex molecules. The magic lies in sulfur's versatility. Unlike many elements, it can exist in multiple states, easily gaining or losing electrons to drive reactions. In volcanic settings, hydrogen sulfide could have donated electrons to convert carbon monoxide into acetic acid, a key component of metabolism. Meanwhile, sulfur dioxide might have absorbed ultraviolet light, using that energy to stitch together formaldehyde molecules into sugars. It's as if sulfur wore multiple hats, sometimes a power source, sometimes a catalyst, always a facilitator. Some of the most compelling evidence comes from underwater vents called white smokers, where mineral towers built of sulfur and calcium carbonate emit milky fluids. These structures, like the Champagne vent off the coast of New Zealand, host thriving microbial communities that derive energy directly from sulfur compounds. Intriguingly, their mineral surfaces often contain microscopic pores that resemble cell membranes, suggesting that sulfur-rich environments didn't just provide chemicals, but physical templates for life's first containers. Yet sulfur's story isn't without controversy. While it excels at jump-starting small molecules, some researchers argue that too much sulfur could have been destructive, breaking apart delicate organics as quickly as it formed them. Others point out that early Earth's sulfur cycle might have been patchy, with productive zones scattered among barren stretches, but this very inconsistency could have been an advantage. Like a cosmic pendulum swinging between creation and destruction, fluctuating sulfur concentrations might have allowed only the hardiest molecules to persist, effectively nature's first quality control. What emerges is a portrait of sulfur not as a passive ingredient, but as an active participant in prebiotic chemistry. From volcanic plumes to deep-sea vents, it could have provided both the spark and the scaffolding for life's first fragile steps. And if that's true, the implications stretch far beyond Earth. Jupiter's moon Io, with its sulfur-spewing volcanoes, or ancient Mars, where sulfate minerals blanket the surface, might have once hosted similar chemical dramas. The universe, it seems, has more than one way to turn a noxious gas into the stuff of life. Phosphorus might not get the same attention as carbon or oxygen when we talk about life's ingredients, but without it, none of us would be here. This unassuming element is the backbone of DNA, the energy currency of cells, and the glue that holds nucleotides together. Yet there's a puzzle scientists call the phosphorus problem on early Earth. Most phosphorus was locked away in insoluble minerals, utterly useless for brewing life's molecules. So how did this critical element break free to join life's recipe? The answer might lie in a rare metallic mineral that didn't come from Earth at all, but from the heavens above, schrebersite, a phosphorus-rich compound found in iron meteorites. When these cosmic bullets slammed into the young planet, they didn't just deliver phosphorus, they delivered it in a form that chemistry could actually use. Unlike Earth's stubborn apatite, which resists dissolving in water, schrebersite is far more reactive. In lab experiments, when scientists simulate the conditions of early Earth by placing schrebersite in acidic water, think volcanic ponds or acidic rainwater, it corrodes, releasing phosphorus ions that readily bond with organic molecules. Even more remarkably, these reactions don't just stop at simple phosphates. They go on to form phosphite and pyrophosphate, compounds that closely resemble the energy-carrying molecules in modern cells. It's as if meteorites didn't just bring phosphorus, they brought it pre-packaged for action, like a cosmic battery ready to power life's first chemical reactions. The evidence for this isn't just theoretical. The famous Murchison meteorite, which we've met before as an amino acid courier, also contains schrebersite. And when researchers soaked fragments of similar meteorites in water mimicking early Earth's conditions, they watched as the mineral transformed into phosphorylated sugars, the very building blocks of RNA. This bridges a gap that's long stumped origin of life researchers. How did phosphate, which tends to be scarce and inert in natural environments, become so central to biology? The answer might be that it didn't have to emerge here at all. It arrived ready-made courtesy of space rocks, but meteoritic phosphorus doesn't just solve the solubility problem, it also offers an elegant solution to energy. Modern cells rely on adenosine triphosphate, or ATP, to shuttle energy around, and ATP's secret weapon is its phosphate bonds. Schrebersite's corrosion products like pyrophosphate are eerily similar. Some scientists suggest that before ATP evolved, meteorite-derived phosphate could have played the same role, giving early life a proto-metabolism to build upon. It's a provocative idea. The energy system that powers every living thing today might trace its roots to the fiery impacts that once scarred our planet. Of course, not all scientists are convinced. Some argue that volcanic environments could have provided alternate phosphorus sources, like the mineral whitlockite, which becomes soluble under extreme heat. Others point out that while schrebersite is reactive, it's also rare. Could there have been enough meteoritic phosphorus to make a difference? But here's the counterpoint. 4 billion years ago, Earth was under constant bombardment. Even if only a fraction of those impactors carried schrebersite over millions of years, the cumulative delivery could have been staggering. And once dissolved, phosphorus doesn't vanish, it cycles, getting reused in countless reactions. The implications stretch beyond our own origins. If meteorites were Earth's phosphorus angels, the same could hold true for Mars or icy moons like Europa. Wherever Schreibersite-rich rocks collided with watery worlds, the seeds of biochemistry might have been sown. It's a humbling thought that an element so vital to our existence might have hitchhiked here on the very rocks we once feared as bringers of doom. Turns out the universe has a way of turning catastrophe into creation, one atomic bond at a time. Cosmic rays, those high-energy particles racing through space at nearly the speed of light, might seem like unlikely architects of life's building blocks. After all, their immense energy is known to shred molecules apart. But here's the twist: destruction and creation often go hand in hand in the cosmos. When these subatomic bullets slam into clouds of gas and dust, they don't just leave chaos in their wake. They trigger a cascade of reactions that could transform simple molecules into the complex organic compounds life needs to begin. Take the Taurus molecular cloud, a sprawling stellar nursery about 450 light-years away. Astronomers studying this region have detected something startling: an abundance of organic molecules like methanol and formaldehyde, floating in spaces so cold and diffuse that conventional chemistry should grind to a halt. So how are these compounds forming? The answer might lie in cosmic rays. As these particles tear through the cloud, they strip electrons from atoms, creating ionized fragments that are desperate to react. Like molecular shrapnel, these fragments collide with neighboring molecules, stitching them together into larger, more complex structures. It's chemistry on fast forward, driven by the universe's most energetic particles. Laboratory experiments back this up. When scientists simulate cosmic ray impacts by firing protons at icy mixtures of water, carbon monoxide, and ammonia, materials common in interstellar clouds, they've watched as simple ices transform into compounds like glycolaldehyde, a sugar linked to the formation of RNA. The process hinges on ionization. A single cosmic ray can knock an electron loose from a molecule, turning it into a chemically reactive ion. That ion then grabs whatever's nearby, whether it's a hydrogen atom drifting by or another broken molecule. Over time, this patchwork assembly can build surprisingly intricate organic chains. But cosmic rays don't just supply energy, they also provide direction. Unlike ultraviolet light, which scatters randomly, cosmic rays travel in straighter paths, creating focused zones of reactivity. In the Taurus cloud, this could explain why certain organic molecules cluster in specific regions, as if the rays are painting chemical hotspots across the void. Even more intriguing, some of these reactions produce molecules with a slight preference for one mirror image form over another, a trait seen in biological molecules on Earth. Could cosmic rays have given life's chemistry its first nudge toward handedness? Yet mysteries linger. While we've seen cosmic rays build small organics in labs, bridging the gap to something as complex as amino acids or nucleobases remains a challenge. And there's the question of delivery. How do these molecules survive the journey from deep space to planets? Some theories suggest they hitch rides inside icy comets, shielded from radiation until they crash into watery worlds like Earth. Others propose that cosmic rays themselves might help, their ionization creating electric fields that gently guide organics toward forming stars and planets. What's clear is that the universe never wastes an opportunity. Even its most violent phenomena, particles launched from supernova, blazing through space with enough energy to obliterate atoms, might quietly be laying the groundwork for life. So the next time you hear about cosmic rays, don't just think of them as interstellar radiation. Think of them as celestial chemists working in the dark, turning the raw stuff of the cosmos into the ingredients of existence. Out in the deepest, coldest reaches of space, where temperatures hover just a few degrees above absolute zero, chemistry shouldn't stand a chance. Reactions we take for granted on Earth, molecules colliding, bonds breaking and forming, require energy. Yet against all odds, astronomers keep finding complex organic molecules in these frozen wastelands. The solution to this paradox might be hiding in plain sight, locked within the structure of ice itself. Tiny grains of ice, no larger than specks of dust, could be serving as cosmic chemistry sets, their crystalline surfaces orchestrating reactions that defy conventional logic. Here's how it works. In the vacuum of space, individual water molecules freeze onto dust particles, building up layers of ice laced with trapped gases like carbon monoxide, methane, and ammonia. At these frigid temperatures, molecules should be frozen in place, unable to overcome the energy barrier needed to react. But quantum mechanics throws a curveball. A phenomenon called quantum tunneling allows particles to cheat, skipping over energy barriers as if they weren't there. Imagine a ball rolling up a hill so slowly it should never reach the top, only to suddenly appear on the other side as if by magic. That's tunneling in action, and on ice grains, it means hydrogen atoms can hop between molecules, rearranging them into new compounds despite the cold. Laboratory experiments have caught this process in action. When scientists recreate interstellar ice conditions in vacuum chambers, chilling mixtures to near absolute zero and irradiating them with ultraviolet light, they've watched simple molecules like formaldehyde morph into glycolaldehyde, a sugar linked to RNA formation. The ice isn't just a passive stage, it's an active participant. Its rigid structure aligns molecules in precise orientations, increasing the odds they'll react when tunneling occurs. Some ices even contain microscopic tunnels and pores, creating sheltered pockets where delicate organics can accumulate without being ripped apart by radiation. But the real kicker, these reactions might explain one of life's great quirks, handedness. Many organic molecules come in mirror image versions like left and right hands. Life on Earth uses just one type, a puzzle that's baffled scientists for decades. Ice grains could hold the answer. When polarized light waves vibrating in a single plane shines on these ices, it interacts differently with each mirror image form, subtly favoring one over the other. Over millennia, that tiny bias could snowball, leaving behind a lopsided mixture of molecules ready to seed planets like Earth. Astronomers have spotted signs of this process in action. The Rosetta mission found the amino acid glycine on comet 67P, while radio telescopes have detected complex organics like ethyl formate responsible for the smell of raspberries in giant molecular clouds. These molecules shouldn't exist in such harsh environments unless something extraordinary is at work. Ice grains, with their quantum quirks and templating surfaces, fit the bill perfectly. Yet mysteries remain. How do these fragile molecules survive the journey from deep space to planetary surfaces? Some might be sheltered inside comets, their icy shells acting like cosmic freezer bags. Others could hitch rides on dust particles, gently drifting down through atmospheres over eons. Whatever the path, the implications are staggering. If ice grains really are universal chemistry sets, then the raw materials for life might be everywhere, quietly assembling in the frozen dark, waiting for the warmth of a newborn planet to wake them up. Around newborn stars, where swirling disks of dust and gas coalesce into planets, there's a hidden alchemy at work, a process that might have filled the cosmos with life's building blocks long before Earth even existed. These protoplanetary disks, observed in stunning detail by telescopes like ALMA, aren't just nurseries for worlds, they're immense chemical factories. Here, ultraviolet light and heat from the young star interact with icy grains and gas molecules, crafting complex organics in regions where temperatures fluctuate wildly. It's a Goldilocks scenario: too close to the star and molecules are vaporized, too far and they freeze into dormancy. But in the intermediate zones where warmth and radiation meet just right, something extraordinary unfolds. ALMA observations of disks around stars like V883 Orionis reveal a treasure trove of organic molecules: methyl cyanide, acetone, even glycolaldehyde, a sugar linked to RNA formation. These aren't scattered randomly. They concentrate in specific rings where icy grains sublimate into gas, releasing trapped compounds into an environment primed for further reactions. The chemistry here operates on a scale that dwarfs anything on Earth. One such disk, spanning billions of kilometers, might contain more organic material than all of Earth's oceans combined. But how does this cosmic kitchen work? The key lies in the interplay between heat and radiation. UV light from the young star breaks apart simple molecules like methane and water, creating reactive fragments. These fragments then collide with other molecules on the surfaces of dust grains, forming larger, more complex structures. It's a bit like molecular Lego. The energy from the star provides the force to snap the pieces together. Meanwhile, heat from the disk's inner regions creates thermal gradients, driving these newly formed organics outward into cooler zones where they can stabilize and accumulate. The real magic happens in the disk's midplane, a shadowy region where starlight barely penetrates. Here, shielded from destructive radiation, organic-laden dust grains clump together, growing into pebbles and eventually planetesimals. Some of these bodies, destined to become comets or asteroids, could carry their chemical cargo intact for billions of years. When they later collide with young planets like Earth, they deliver not just water, but a pre-made toolkit for life. Critics often argue that the intense radiation near stars should annihilate delicate organics, but nature has a workaround. Observations show that molecules like formaldehyde and methanol often form protective ice mantles around dust grains, shielding their cores from UV damage. These icy shells act like molecular bunkers, preserving the goods until they reach safer environments. And when the star's outbursts, violent flares common in youth, blast the disk with extra energy, they might actually accelerate the synthesis of even more complex compounds. What's startling is how quickly this all unfolds. Protoplanetary disks typically last only a few million years, a blink in cosmic time, yet ALMA data proves they can assemble molecules as intricate as dimethyl ether, a precursor to more complex organics in that short span. This efficiency suggests that the universe doesn't need eons to lay life's groundwork. Given the right conditions, it can happen at breakneck speed. The implications ripple far beyond our solar system. If every young star's disk is a potential organic factory, then the raw materials for life might be a default feature of planet formation. From the TRAPPIST-1 system's rocky worlds to the distant exoplanets of the Orion Nebula, the same processes could be unfolding right now, silently stocking the galactic pantry with the ingredients for biology. It's a humbling thought that the same forces shaping worlds might also be sowing the seeds of life, one molecule at a time. Picture a steamy geothermal pool on early Earth, its waters bubbling with chemical potential. As the sun beats down, the pool's edges slowly evaporate, shrinking the liquid into smaller, more concentrated pockets. Then comes a rainstorm, refilling the basin, only for the cycle to repeat days or weeks later. This back and forth between wet and dry might seem mundane, but it could be one of nature's most ingenious tricks for coaxing simple molecules into the complex structures life needs. Recent lab experiments reveal that these cycles don't just concentrate organics, they actively drive them toward complexity, like a molecular boot camp where each round of training builds stronger bonds. Take the work of researchers at the Foundation for Applied Molecular Evolution, who recreated these conditions in glass dishes. They started with amino acids, the same compounds found in meteorites and hydrothermal vents dissolved in water. Then they mimicked geothermal cycling by gently heating the solution to evaporate water, leaving behind a concentrated film. When they rehydrated the mixture, something remarkable happened. The amino acids didn't just dissolve back in, they linked up into chains called peptides, the precursors to proteins. Over multiple cycles, these chains grew longer and more stable, as if the pool itself was teaching chemistry how to polymerize. The magic lies in the physics of drying. As water evaporates, it forces molecules closer together, increasing the chances they'll react. But it's not just about proximity. The drying process also removes water molecules that can interfere with bond formation. In chemistry terms, water is a byproduct of peptide formation, so removing it pushes the reaction forward, like a seesaw tilting toward complexity. Add in the minerals often found in geothermal pools, clays, sulfides, or metal ions, and suddenly you've got a catalytic environment where each cycle ratchets the system toward greater sophistication. But geothermal pools offer more than just chemistry. Their physical structure creates microenvironments like a series of tiny test tubes. As water levels fluctuate, different zones emerge, shallow edges where concentration happens fastest, deeper centers where molecules can mix, and mineral-rich boundaries where surfaces might template specific reactions. This patchwork of conditions means that even if one reaction fails in one spot, it could thrive in another. It's a built-in redundancy, allowing the system to explore countless chemical pathways without dead ending. Critics point out that while wet-dry cycles excel at making peptides, bridging the gap to something like RNA, a molecule many consider essential for life's origins, remains a hurdle. Yet recent breakthroughs suggest these cycles might be more versatile than we thought. In 2020, a team at the University of Strasbourg demonstrated that similar conditions could promote the formation of nucleobases, RNA's building blocks, and even encourage them to link into short strands. The key was including boron-rich minerals which stabilize ribose, RNA's sugar component, long enough for it to integrate into larger molecules. What's tantalizing is how universal this process could be. Geothermal pools aren't unique to Earth, Mars' ancient hot springs, or Saturn's moon Enceladus, with its subsurface seafloor vents, might have hosted similar cycling. And the timescales align perfectly. Early Earth's day was shorter, meaning faster tides and more frequent rainfall, potentially accelerating these cycles into hyperdrive. Over millennia, that rhythmic pulsing evaporate, concentrate, rehydrate could have turned a handful of simple compounds into a library of molecular possibilities, each pool a potential cradle where chemistry inched toward biology. So next time you see a steaming hot spring, don't just admire its beauty. Imagine it 4 billion years ago, a crucible where the mundane dance of evaporation and rainfall might have quietly written the first drafts of life's code, one droplet at a time. Deep beneath the ocean surface, where volcanic heat meets mineral-rich fluids, an unassuming metallic crystal might hold the secret to life's origins. This is the heart of Gunther Wechtersheuser's iron-sulfur world theory, a bold idea that life didn't begin in open water or primordial soup, but on the jagged, conductive surfaces of iron pyrite, better known as fool's gold. At first glance, pyrite seems inert, just a shiny mineral common in Earth's crust. But Wechtersheuser saw something revolutionary. Its positively charged surface could act as a cosmic charging station, attracting negatively charged molecules like carbon dioxide and knitting them together into life's first organic compounds. The brilliance of this theory lies in its self-sustaining chemistry. Pyrite forms when iron reacts with hydrogen sulfide, releasing energy in the process. Wechtersheuser proposed that this same reaction could have powered the synthesis of organic molecules, with the mineral surface acting as both catalyst and energy source. Picture a hydrothermal vent's rocky wall crusted with pyrite crystals. As hot, acidic fluids surge past, carbon dioxide in the water gets pinned to the pyrite surface, where it reacts with hydrogen to form acetic acid, a molecule central to modern metabolism. This isn't just speculation. Lab experiments have confirmed that pyrite can indeed catalyze these reactions, with some studies producing not just acetic acid but also pyruvate, a critical compound in cellular energy cycles. Yet the iron-sulfur world offers more than just molecule building. It provides a potential pathway to complexity. Pyrite's crystalline structure creates tiny, geometric pits perfect for trapping and concentrating organic molecules. Over time, these clusters could have grown more intricate, eventually forming primitive metabolic networks right on the mineral's surface. Some researchers compare this to a molecular assembly line, with pyrite's conductive properties allowing electrons to flow between reactions like a primitive form of cellular respiration. Modern support for this theory comes from unexpected places. Deep sea vents like the Lost City field are rich in iron-sulfur minerals, and their porous chimneys resemble the mineral matrices Wechtershauser envisioned. Even more compelling, certain ancient proteins at the heart of modern biology like ferredoxins, which shuttle electrons in cells, contain iron-sulfur clusters at their core. It's as if life retained a molecular fossil of its mineral beginnings long after leaving the rocky cradle. Critics, however, highlight gaps. While pyrite excels at small molecule synthesis, bridging the gap to polymers like RNA remains a challenge. Others argue that iron-sulfur reactions might be too slow to compete with other prebiotic environments, yet recent advances have breathed new life into the theory. Experiments combining pyrite with peptides show the mineral can help link amino acids into longer chains, while studies of Martian meteorites reveal similar iron-sulfur minerals capable of organic catalysis. The debate isn't settled, but one thing is clear. What began as a radical hypothesis has grown into a foundational thread in the tapestry of origins research, a reminder that sometimes the most ordinary rocks hide extraordinary secrets. Formamide might sound like an obscure lab chemical, but this simple molecule, just hydrogen, carbon, oxygen, and nitrogen, could be the unsung hero of life's molecular origins. Imagine a scenario where all the ingredients for RNA, the molecule many scientists believe predated DNA in early life, could emerge from a single, unassuming substance. That's the radical promise of formamide. Under the right conditions, whether bathed in ultraviolet light or simmered with volcanic minerals, this liquid transforms into a one-pot kitchen where nucleobases, sugars, and even amino acids cook up together. It's like discovering a universal starter mix where all you need to add is energy, and the universe hands you the building blocks of biology. The chemistry behind this is as elegant as it is powerful. Formamide's structure, a nitrogen atom linked to a carbon-oxygen backbone, makes it a versatile springboard for complexity. When zapped with UV radiation like that from the young sun, its molecules break apart into reactive fragments. These fragments don't just drift away, they recombine into more elaborate structures. In lab experiments mimicking early Earth conditions, scientists have watched formamide solutions yield adenine, guanine, and uracil-3 of the 4 nucleobases found in RNA. Even more astonishing, the same reactions can produce ribose, the sugar that forms RNA's spine. It's as if formamide holds a hidden blueprint, waiting for the right trigger to unfold into life's essential code. Heat works just as well as light. In experiments where formamide is heated with minerals like clays or meteoritic dust materials common on the early Earth, the results are equally dramatic. At around 160 degrees Celsius, formamide begins stitching itself into nucleobases with startling efficiency. Some studies even report the formation of carboxylic acids, the precursors to amino acids. This thermal pathway suggests that geothermal areas like volcanic ponds or hydrothermal systems could have been ideal formamide kitchens. The molecule's stability at high temperatures means it wouldn't vaporize immediately, giving reactions time to build complexity before conditions cool. But formamide's true genius lies in its synergy. Unlike theories that require separate processes to make nucleobases and sugars, each needing different conditions, formamide unifies them. In a 2018 experiment, researchers at the University of Strasbourg demonstrated that when formamide interacts with borate minerals, it not only generates nucleobases but also stabilizes ribose long enough for the two to combine into something resembling a primitive nucleotide. Borates, which likely existed in early Earth's alkaline lakes, act like molecular babysitters, preventing ribose from breaking down before it can link up. This solves one of the trickiest puzzles in origin of life research: how fragile sugars survived long enough to join the party. Critics argue that while formamide reactions work beautifully in labs, its concentration in natural settings might have been too low to matter. After all, today's formamide is rare outside industrial settings, but 4 billion years ago the story could have been different. Volcanic outgassing, asteroid impacts, and even interstellar ice delivery might have enriched formamide in certain environments like tidal pools or geothermal craters. Some computer models suggest that ultraviolet light acting on atmospheric hydrogen, cyanide, a compound detected in comets, could have rained formamide into surface waters over millennia. Perhaps the most compelling evidence comes from beyond Earth. The Rosetta mission detected formamide on comet 67P, while radio telescopes have spotted it in star-forming regions like Orion's belt. If this molecule is floating between stars and hitching rides on cosmic iceballs, then its potential to seed chemistry isn't just an earthly fluke, it's a universal possibility. Formamide's story challenges us to rethink simplicity. Sometimes the most ordinary-looking substance holds the keys to extraordinary complexity, quietly waiting for the right moment to reveal its role in the grand narrative of life. Hydrogen cyanide, a molecule infamous as a deadly poison, might have been one of life's most unlikely midwives. In the swirling chaos of Earth's early atmosphere, this simple compound, just 3 atoms linked together, could have played a starring role in crafting adenine, one of the 4 key building blocks of DNA and RNA. The chemistry behind this transformation is as elegant as it is surprising. When hydrogen cyanide molecules collide in the presence of water and ultraviolet light, they undergo a series of reactions that culminate in adenine's intricate ring structure. It's like watching a cosmic origami artist fold a single sheet of paper into an elaborate sculpture, except here, the paper is a toxic gas and the sculptor is the raw energy of a young planet. Lab experiments dating back to the 1960s demonstrate this process in stunning detail. Researchers mixing hydrogen cyanide with ammonia and water, then exposing the solution to UV light or heat, watched as adenine emerged spontaneously. Even more remarkable, these reactions don't just produce tiny traces under the right conditions. Adenine forms in substantial quantities, as if the universe has a hidden preference for this molecule. Some studies suggest that freezing hydrogen cyanide solutions might boost the yield further, as the slow concentration of molecules in icy matrices increases their chances of colliding and reacting. This could mean that wherever hydrogen cyanide pooled, whether in evaporating tidal lagoons or icy cometary deposits, adenine might have been quietly accumulating, ready to join life's molecular toolkit. Yet the hydrogen cyanide theory isn't without controversy. The biggest hurdle, concentration. For these reactions to work efficiently, early Earth's atmosphere would have needed far more hydrogen cyanide than current models suggest existed. Critics argue that without a methane-rich atmosphere, a feature of the classic Miller-Urey setup, that newer research disputes hydrogen cyanide levels might have been too low to matter. But here's where nature's ingenuity shines through. Recent studies propose that temporary hotspots could have solved this puzzle. Volcanic plumes, meteorite impacts, or even lightning strikes might have created localized pockets where hydrogen cyanide concentrations spiked, allowing bursts of adenine synthesis before the gas dispersed. Imagine a chain of tiny chemical factories scattered across the planet, each one briefly humming with activity before fading back into the background. Another twist comes from extraterrestrial delivery. Comets and carbonaceous meteorites often contain hydrogen cyanide frozen within their icy interiors. When these objects bombarded early Earth, they wouldn't just have delivered pre-made organics, they could have been hydrogen cyanide grenades, releasing their volatile cargo upon impact. Simulations show that the heat and pressure of such collisions might have catalyzed the formation of adenine right then and there, as if the impact itself was the spark that lit the chemical fuse. What makes this theory so compelling is its dovetailing with the RNA world hypothesis. adenine isn't just a DNA component, it's a key player in ATP, the molecule cells use for energy, and in coenzymes essential for metabolism. If hydrogen cyanide really did pepper the early Earth with this versatile compound, it wouldn't just have provided a genetic letter, it might have supplied the energy currency and chemical tools needed to kickstart the whole system. Debates over hydrogen cyanide's role remind us that life's origins likely weren't a single eureka moment, but a mosaic of processes, each contributing pieces to the puzzle. Whether through atmospheric chemistry, icy concentration, or cosmic impacts, this deceptively simple molecule illustrates a profound truth. Sometimes the things we fear most hold the keys to our very existence. What if life's earliest molecules didn't emerge alone, but as partners, peptides and nucleotides dancing together from the very beginning? This is the provocative idea behind peptide-nucleotide coevolution, a theory that challenges the long-standing RNA world hypothesis by suggesting these two molecular families evolved in tandem, each shaping the other's destiny. At its core, this idea flips the script on origins research. Instead of asking which came first, proteins or genetic material, it proposes they arose simultaneously, bound together by the unsung hero of prebiotic chemistry, minerals. Picture a volcanic shoreline 4 billion years ago where tidal pools ebb and flow over porous, mineral-rich rocks. Here, nucleotides, the building blocks of RNA, might have adhered to charged mineral surfaces like clay or pyrite, aligning in neat rows. Nearby, amino acids drawn to the same substrates could have linked into short peptides under the sun's ultraviolet glare. But here's the twist: minerals like montmorillonite don't just organize these molecules, they mediate conversations between them. Lab experiments show that when nucleotides and amino acids coexist on mineral surfaces, peptides can act as scaffolds, stabilizing fragile RNA strands, while RNA's negative charge helps peptides fold into functional shapes. It's a symbiotic relationship written in atomic attraction, where neither molecule could advance without the other. The implications are staggering. If peptides and nucleotides co-evolved, it solves two of the RNA world's biggest puzzles: how RNA replicated without enzymes, traditionally a protein job, and how proteins gained specificity without genetic instructions. In this model, rudimentary peptides might have acted as primitive catalysts, accelerating RNA's self-replication, while RNA's ability to store information could have guided peptide sequences. Minerals would be the matchmakers, their surfaces providing both a stage and a script for this molecular tango. Evidence for this synergy hides in plain sight within modern biology. The ribosome, life's universal protein factory, is essentially a RNA-peptide hybrid, its catalytic core made of RNA wrapped in supportive proteins. Even ATP, the energy currency of cells, is a nucleotide with a peptide-like tail, as if echoing an ancient partnership. Supporters of coevolution argue these aren't coincidences but molecular fossils, remnants of a time when the line between genetic and functional molecules was blurred. Critics counter that such complexity seems unlikely in prebiotic chaos, but recent experiments offer startling support. In 2022, a team at the Scripps Research Institute demonstrated that amino acids and nucleotides, when mixed with volcanic glass and mild heat, form co-assemblies where peptides help RNA chains extend, and vice versa. Even more compelling, these assemblies exhibit a primitive form of encoding where specific peptides correlate with RNA sequences, hinting at the birth of genetic memory. The debate is far from settled, but peptide-nucleotide coevolution reframes life's origins as a collective effort, where molecules, minerals, and environment conspired to cross the threshold into biology. It suggests that life's first language wasn't RNA or proteins alone, but a pigeon of both, a dialect lost to time but preserved in every cell's core machinery. And if that's true, the path to life might not be a solitary ladder but a winding bridge, built together stone by stone. At Earth's poles, where temperatures plunge far below freezing, something extraordinary happens to molecules trapped in ice. They don't just sit there, they rearrange. The theory of polar ice synthesis suggests that life's building blocks didn't need scorching vents or lightning strikes to form. They could have been crafted in the quiet cold, where freezing acts like a molecular sculptor, squeezing and organizing simple compounds into complex ones. Picture an ancient glacial pond on early Earth, its surface crusted with ice, but underneath, a hidden alchemy unfolds. As water freezes, it purifies itself, pushing impurities like dissolved organics into concentrated pockets between ice crystals. In these microscopic chambers, molecules that would normally drift apart in open water are forced into close quarters, dramatically increasing their chances of reacting. Antarctica offers a stunning modern analog. Scientists studying icy brine pools there have discovered surprisingly complex chemistry happening even at -20 degrees Celsius. When seawater freezes, it expels salts and organic material into super-concentrated liquid veins thinner than human hair. In these tiny channels, reactions that would take years in open water can occur in days. Lab experiments confirm this when researchers freeze mixtures of ammonia and cyanide, a cocktail thought to exist on early Earth. They've watched as adenine, a key component of DNA and RNA, forms efficiently. The cold doesn't just preserve, it actively assembles, but the magic of ice goes beyond concentration. Its crystalline structure plays architect too. As ice forms, its lattice-like arrangement can align molecules in precise orientations, like a cosmic choreographer ensuring partners meet at the right angle for bonding. Some studies suggest that ice's surface might even mimic the behavior of enzymes, lowering the energy needed for reactions. This could explain how glycine, the simplest amino acid, has been found in interstellar ice analogues. No heat required, just the patient geometry of freezing. The implications extend beyond Earth. Europa, Jupiter's icy moon, or Saturn's Enceladus, with their subsurface oceans and icy crusts, might be hosting similar processes right now. Ice isn't just a barrier on these worlds. It could be a factory, its slow, rhythmic freeze-thaw cycles quietly assembling the ingredients for life in the dark. So next time you see frost on your window, consider this. The same force that paints delicate patterns on glass might have once woven the first threads of life's tapestry, one frozen moment at a time. Deep beneath the ocean's crushing pressures or trapped within Earth's crust, carbon dioxide behaves in a way that defies ordinary chemistry. It becomes supercritical, a state where it's neither fully gas nor liquid but something in between. This strange form of CO2, often overlooked in origin of life theories, might have been the universe's secret solvent, crafting life's molecules with a finesse no other medium could match. Picture a hydrothermal system where temperatures soar past 31 degrees Celsius and pressures exceed 74 times Earth's surface level. Here, CO2 transforms, gaining the dissolving power of a liquid and the penetrating ability of a gas, all while remaining gentle enough to preserve delicate organic structures. It's like a molecular Goldilocks zone where reactions happen faster and more selectively than in water alone. Laboratory experiments reveal supercritical CO2 astonishing versatility. When scientists simulate deep-sea conditions, they've watched as this fluid dissolves fatty acids, key components of cell membranes, then arranges them into stable vesicles, tiny bubbles that mimic primitive cells. Unlike water, which can disrupt these assemblies with its polar charges, supercritical CO2 provides a neutral playground where hydrophobic molecules like lipids can organize without interference. Even more striking, this medium excels at stitching together amino acids into peptides, thanks to its ability to concentrate reactants while excluding water molecules that might otherwise break the bonds. It's as if nature had a stealthy architect working in the shadows to assemble life structures without the chaos of aqueous chemistry. The real magic lies in supercritical CO2 dual nature. Its gas-like diffusivity allows it to penetrate microporous minerals, carrying organics deep into protective rocky matrices where they can accumulate. Yet its liquid-like density enables it to dissolve and transport larger molecules than any gas could. This combination could have turned underground fissures or subsea vents into molecular assembly lines, with CO2 shuttling ingredients between mineral catalysts and sheltered reaction chambers. Modern industry harnesses these properties for everything from decaffeinating coffee to pharmaceutical synthesis. Why wouldn't nature have exploited them first? Critics argue that supercritical CO2 narrow pressure temperature range limits its plausibility as a widespread prebiotic solvent. But early Earth offered no shortage of extreme environments, subduction zones, deep crustal pockets, or even the high-pressure interiors of icy comets could have hosted these conditions. And here's the twist: supercritical CO2 doesn't need to act alone. Recent studies show it pairs brilliantly with water, forming interfaces where polar and non-polar reactions can occur simultaneously, like a two-zone kitchen where soups and oils cook side by side without mixing. Perhaps the most tantalizing clue comes from modern extremophiles. Microbes thriving in deep-sea vents like the Lost City don't just tolerate CO2, they depend on it, using enzymes optimized for carbon dioxide-rich environments. Could this be an echo of life's origins, a biochemical relic of a time when supercritical CO2 wasn't just a bystander, but the stage itself? The theory remains young, but it challenges us to rethink our water-centric view of life's beginnings. After all, if the universe can craft life's blueprints in the most unexpected solvents, then the recipe for existence might be far more flexible and far more ingenious than we ever imagined. Earth's magnetic field is an invisible shield, deflecting cosmic rays and solar winds that would otherwise strip away our atmosphere. But what if this force did more than just protect? What if it actively shaped the chemistry that led to life? The idea that our planet's magnetism might have played a role in organizing life's building blocks is speculative but tantalizing. Picture the young Earth, its magnetic field flickering and forming as molten iron churned in its core. This wasn't just a barrier, it was a dynamic, fluctuating force that could have subtly influenced the behavior of molecules across the planet's surface. Laboratory experiments reveal that magnetic fields can alter chemical reactions in surprising ways. Certain molecules, particularly those with unpaired electrons like free radicals, are sensitive to magnetic forces. When exposed to even moderate fields, these molecules can align in specific orientations, changing how they interact with each other. Some studies have shown that magnetic fields can accelerate reactions involving oxygen or sulfur, while others suggest they might influence the way amino acids form chains. On early Earth, where organic molecules were scattered and dilute, this gentle guidance could have been the nudge needed to steer chemistry toward complexity. Imagine tidal pools or hydrothermal vents bathed not just in heat and minerals, but in the quiet pull of Earth's magnetism, aligning molecules just enough to tip the scales toward reactions that wouldn't happen otherwise. The strongest case for this theory lies in the peculiar behavior of chiral molecules, those that exist in mirror image forms. Life on Earth overwhelmingly uses one version of these molecules, a mystery known as homochirality. Magnetic fields combined with other forces like polarized light might have provided the slight bias needed to favor one form over the other. Experiments with amino acids in strong magnetic fields have shown small but measurable differences in how left and right-handed versions react. Over millions of years, even a tiny preference could have snowballed into the uniformity we see in biology today. Yet the evidence remains frustratingly sparse. Earth's early magnetic field was likely weaker and less stable than it is now, and without a time machine, we can't measure its exact influence on prebiotic chemistry. Critics argue that any magnetic effects would have been dwarfed by more powerful forces like volcanic heat or ultraviolet radiation. But here's the intriguing counterpoint. Magnetism doesn't need to act alone. It could have worked in concert with other factors, amplifying their effects. For example, a magnetic field might have enhanced the catalytic properties of iron-rich minerals near hydrothermal vents, or guided charged particles in the atmosphere to create localized hotspots of organic synthesis. One of the most provocative suggestions is that Earth's magnetism didn't just influence chemistry, it might have created physical structures where life could emerge. Scientists studying ferromagnetic fluids, liquids filled with tiny magnetic particles, have watched them spontaneously form intricate shapes under magnetic fields, from swirling vortices to geometric lattices. If certain prebiotic solutions contained similar particles, Earth's field could have sculpted them into microscopic compartments where molecules were concentrated and protected, much like the pores in rocks or the bubbles in sea foam. These transient structures wouldn't leave fossils, but they could have provided the temporary order needed for life's first fragile experiments. The challenge with this theory is its invisibility. Unlike meteorites or hydrothermal vents, magnetism leaves no direct chemical signature in ancient rocks. Yet its potential role is too compelling to ignore, especially when we look beyond Earth. Mars once had a magnetic field, and its disappearance coincided with the loss of its atmosphere and water. Coincidence or a clue that magnetism does more than we think? Even if the evidence is elusive, the idea pushes us to reconsider the subtle forces that might have quietly shaped life's origins. After all, nature rarely relies on just one tool. If volcanoes, lightning, and comets each played a part, why not the silent, steady hand of Earth's magnetic field, humming in the background as life took its first uncertain steps? Quantum tunneling bends the rules of chemistry as we know them, defying logic by allowing particles to cheat their way through energy barriers that should be impossible to cross. At temperatures just above absolute zero, where molecules should be frozen in place, quantum mechanics takes over, enabling reactions that classical physics says shouldn't happen. Picture a snowball rolling up a hill without a push, or a marble phasing straight through a wall. That's the bizarre beauty of tunneling. Particles don't need enough energy to surmount an obstacle. They can simply tunnel through it, vanishing on one side and reappearing on the other. In the icy depths of space, this phenomenon might explain how complex organic molecules emerged in environments where chemistry should be comatose. Astrochemists have long puzzled over the presence of molecules like methyl formate and glycolaldehyde in frigid molecular clouds, where temperatures hover around -260 degrees Celsius. Classical models predict these reactions would take billions of years, far longer than the age of the universe itself. Yet telescopes detect them everywhere. The answer lies in tunneling. Hydrogen atoms, the lightest and most quantum-ambitious particles, can skip through energy barriers like ghosts, enabling reactions between ice-coated dust grains that would otherwise never occur. Lab experiments simulating these conditions have caught hydrogen atoms in the act, watching as they tunnel into position to transform carbon monoxide into formaldehyde, or stitch methanol into more complex sugars. It's chemistry without heat, without light, just the quiet, probabilistic magic of quantum mechanics. The implications are staggering. If tunneling helped forge life's precursors in the coldest corners of space, then the universe's recipe for organic molecules isn't limited to balmy planets or scalding vents. Even Pluto's frozen plains or Europa's subsurface glaciers could host this shadow chemistry, their ices whispering reactions into existence one quantum leap at a time. Some researchers take this idea further, suggesting tunneling might have influenced life's most puzzling asymmetry. Why all known biology uses only left-handed amino acids and right-handed sugars? Quantum effects combined with polarized starlight or magnetic fields could have introduced a slight bias, amplifying one chiral form over another across eons of icy synthesis. But the wildest fringe of this theory goes further still. What if quantum tunneling didn't just facilitate reactions? What if it actively selected for the molecules that would become life's building blocks? In certain icy matrices, tunneling rates vary wildly depending on molecular shape, meaning the universe might have been subtly favoring specific configurations long before Darwinian selection took over. It's a dizzying thought. The same quantum quirks that power modern electronics could have, in a sense, been life's first editor, sifting possibilities in the dark before biology even began. As telescopes peer deeper into molecular clouds and labs refine their quantum ice experiments, one thing becomes clear: the cold void of space isn't inert. It's a hive of improbable reactions where the rules we know are merely suggestions and particles dance to the hidden tune of quantum probability. Whether this fringe idea holds up or not, it forces us to rethink the boundaries of chemistry and wonder what else might be possible when the universe plays by its own rules. From fiery volcanic vents to the frozen silence of deep space, from the electric fury of lightning to the quiet patience of mineral surfaces, what's striking about these 30 theories isn't just their variety, but how many of them might be true at once. The universe doesn't play by simple rules, and the birth of life's first organic molecules was likely less a single event than a symphony of processes, each contributing a note to the grand composition. Maybe amino acids rained from the sky and bubbled up from hydrothermal vents. Perhaps RNA's building blocks assembled on interstellar ice grains and in evaporating tidal pools. The beauty of this mystery is that the answer probably isn't either / or it's all of the above, a messy, magnificent tapestry of chemistry and chance. Think about it like baking a cake. Flour alone isn't enough. You need eggs, sugar, heat, and time. Similarly, life's ingredients might have required cosmic deliveries plus Earth's unique geology plus the perfect energy sources, all stirred together over millions of years. Some theories even suggest that certain molecules could only form in space, while others needed planetary conditions to stabilize. It's as if the universe had to check multiple boxes before life could even begin to whisper. So which theory speaks to you? Do you picture a lightning-struck primordial soup, or do you lean toward the elegance of alkaline vents? Maybe the idea of quantum tunneling in icy space clouds sparks your imagination, or perhaps you're drawn to the radical simplicity of formamide's one-pot chemistry. The fact that scientists still debate these ideas isn't a weakness, it's a testament to how many paths nature might have taken. And here's the thrilling part: we're still discovering new pieces of the puzzle. Every meteorite analyzed, every lab experiment, every probe sent to distant worlds could rewrite the story. This isn't just about the past either. If life's building blocks form readily across the cosmos, then the universe might be brimming with potential, waiting for the right conditions to awaken. That's why this search matters. It's not just about where we came from, it's about how alone we really are in the void. So what do you think? Drop your favorite theory in the comments, or better yet, propose one we haven't covered. After all, science is a conversation, and the next big idea might just come from someone staring at the stars, wondering how it all